Hey guys, today we're going to learn about electric potential and electric potential energy and what it can do for you. So I wanted to begin, before I launch straight into electric potential, with a question which we might imagine, based on what we know from last unit in electric fields and forces, that we would be able to answer. All right? And we're going to show actually, no, really there's not enough to go off of here in order to answer the question as stated. We can get some parts of it, but actually there's significant pieces which are impossible to answer from what we currently know about electric fields and forces. Okay, meaning us, not scientists in general. Okay, so imagine this scenario. You've got a 200 microcoulomb charge here and a 20 microcoulomb charge there. Whatever, I'm not going to actually work through the numbers, I just had to put some labels on them. Let's say that they start off a meter apart, okay, and I want to know what's the force on the 20 microcoulomb charge. Well, we can solve that. That's just Coulomb's law, right? K/Q over R squared, right? No problem. We could plug in numbers hypothetically and come up with the force that they exert on each other. All right, what is its acceleration? All right, well, that's actually a question that I mostly didn't ask last unit, to a certain extent because it's not usually that helpful unless we happen to be able to do this. Meaning the electric field is uniform. Point charges don't make uniform electric fields. And the trouble there is going to be that the acceleration that we could calculate by, setting these two equal to each other is actually just going to be an initial acceleration. So that when we get to part C and I ask what's the final speed, meaning, when it reaches this point 2 meters further over, we can't actually work that out using kinematics. You might imagine, well, I'll just use the time-independent equation, right? V squared equals V naught squared plus 2a delta x. Seems like this ought to work. The problem is that as the distance increases between these two charges, the force decreases, and therefore the acceleration decreases, which means this equation will not work. Ooh. Oh man, if only there were some way to do this. You know what this reminds me of? This reminds me of a curved ramp problem. Curved ramp problem. In a curved ramp problem, you have, let's say something starts up here and there's a particular slope right here, right? And we could go all the way back to, just linear kinematics and forces and do, the whole mg sine theta thing. Let's say there's no friction, just for simplicity, right? mg sine theta equals ma, and we get the acceleration at the moment that it starts off. But as it rolls or slides down or whatever, and gets to there, okay, the acceleration is going to have a different value. And we said, actually, with these, you can't use kinematics to work out what the speed is going to be at the bottom. It's impossible. It's not impossible. You could do some awful calculus to work it out, but it would just be awful calculus for absolutely no reason, because it turns out, if you recall, there's a much simpler way to get the final speed of the object at the bottom. All right, if you're not sure what it is, rack your brains for a moment. Pause the video, rack your brains before I tell you. The answer is energy. Sure. Starts off here with gravitational potential energy. Ends up down here at the bottom with kinetic energy. And it really doesn't matter what happens in the meantime. It could be a straight ramp, it could be a curved ramp, it could be a wavy ramp, and we would work it out exactly the same way. All that actually matters is, for these purposes, the change in elevation. All right. Now, there's an analogous thing which is going to happen with charges, and that analogous concept is electric potential. It's approximately the same idea as change in height, although obviously not exactly the same because this is not the same, right? Charges, okay? But it's at least an analogous concept. All right, let me bring the other board over here. So if we can't use forces and kinematics to work things out, energy then is usually the solution. So for electric potential energy, we won't usually talk about potential energy, or at least not as frequently. We're more often going to talk about this other term, which is electric potential. Electric potential is represented by, it's measured in volts, represented by the letter V, unsurprisingly. But it's also the same thing as a joule per coulomb. Okay, so it's related to energy, but it's not exactly the same thing as energy, right? Different concepts, right? But they are very clearly related to each other. On your notes packet, there's an equation that directly relates them, which is this one. We'll talk about how to use this in a little bit, okay? Also, when you're trying to calculate electric potential, there's an equation also on your notes packet, which we will also talk about how to use in a little bit. I just wanted to throw these equations up here so that you could have them presented to you as these are important equations, all right? Okay, now, probably the next thing is let's talk about where this unit comes from and also some of the annoying stuff. An annoying thing. This is the letter U. This is the letter V. I will often have to use a U and a V in the same problem. When we say U, we're talking about potential energy. When we say V, we're talking about potential. Okay, so potential or potential difference, when you see the delta in front of it, it's a potential difference. Potential difference is measured in volts. But if I solved this equation for volts, it would be delta U over Q. All right, delta U, that's energy. Energy is measured in, let me hear it now. Ah, yes, you said joules. At least I hope you said joules. And charge, just like last unit, is measured in coulombs. All right, so a volt then is a joule per coulomb. All right, now, what about this analogy that we started talking about on the previous board? Like, how is a curved ramp like electric potential? All right, so on the curved ramp here, right, you can see we've got between two positions of the same height on this ramp, the same change in gravitational potential energy. All right, but different slopes, different rates of change in height. The height is analogous to voltage. The slope is analogous to electric field. All right, so if I come over here now and I say this is actually what it's like, all right, you can see, or you should be able to see here, I've drawn a point charge in the middle here. It's labeled Q. Whatever Q is, it's some number. And then around that, I've drawn a dotted line. And then some more dotted lines, right? Make kind of a bullseye sort of a thing. When we calculate electric potential using this equation right here, what it's going to tell us is that at some particular distance away from a point charge, the potential has a particular value. It doesn't matter whether you're talking about above or below or to the left or the right, it's just how far away from it are you looking at. Okay, so maybe for this particular charge, if we're here, I don't know what that is, 2 centimeters or something, whatever, the potential at any point this distance away is, I wrote in blue, 6,000 volts. All right, if that sounds like a lot, and we'll discover it's maybe not that much unless you're talking about coming out of an electrical outlet. Okay. All right. On this next set of dots, a greater distance away, the potential is only 4,500 volts. So it's at a lower potential. All right. Another dot away, or set of dotted lines away, these ones are at 3,000 volts, so even lower because they are further away. And finally out here I drew 1,500 volts, right? We could keep going, right? The further away you get, according to this equation, the lower the potential is going to be. All right, now if I represent this instead of this way, but more as like a topographical or elevation map, right? At this elevation, which corresponds to this spot right here, we've got 6,000 volts. At a greater distance away, we are at a lower elevation, so to speak, of 4,500 volts. Further away, we're now down to 3,000 volts. All right, and we keep on going, right? The further away you get from this, the lower the potential is getting. By analogy, it's like a change in height, right? So if we had, go back over to here, something roll down some amount of height, that would correspond to a particular amount of gravitational potential energy. That's true, meaning that the change in gravitational potential energy is the same between any 2 points on this track that are the same height away from each other. All right? Meaning, if I had a charge move from the 6,000 volt line to the 4,500 volt line, that is a change in potential of 1,500 volts. It's the same change in potential going from the 4,500 volt line to the 3,000 volt line, even though it's a greater distance, right? Because it's the same change in potential, same change in volts. All right, so same amount. Okay, so to hopefully maybe put it together then, the change in energy, change in also potential, is the same between here and here as it is between here and there, because it's 1,500 volts between any of those points. Because it's a different distance, however, we can say that the rate at which the potential is changing is different, and that corresponds to the magnitude of the electric field. A little more real now, as opposed to sort of abstract with all the graphs and stuff. If you get out a AAA battery, it's a little large for a AAA battery, but bear with me, and a D cell, and you look at them, you will discover the AAA battery and the D cell are both only 1.5 volts. So if you're looking at that and you're like, what the heck? They're both 1.5 volts. What am I paying all this extra money for the D cell if it provides me the same number of volts as a AAA battery? Well, if you're thinking that, you're like most people, you're thinking about potential sort of in the wrong way, all right? 1.5 volts means the battery will do 1.5 joules of work per coulomb of charge that passes through it, meaning that it pushes around, okay? The amount of work that it does is proportional to both this and the amount of charge that it moves, all right? So let me rewrite this equation up here. The difference between this battery and this battery isn't delta V, right? They are both 1.5 volts. The difference is the amount of energy stored in them. There are more chemicals in this, which means that it will ultimately move more charge Q around, okay? More coulombs of charge will pass through this than will pass through this one. And so ultimately this one does more work and provides you with more energy than the smaller battery does, even though they're technically at the same potential because they're going to move a different number of volts around. All right, now what you should do next is look at example 1 and also at the explanation document, which you should be able to find in the drive. All right, hope that was helpful, guys.